Why is almost everything in the universe round? And I mean really round. Planets, stars, moons, even black holes have spherical event horizons. Now, before we go any further, I want you to think about this for a second. Look around your room right now. You probably see a lot of things that aren't round. Your desk, your chair, your computer screen, the walls around you. Everything's made of angles and flat surfaces. But zoom out, way out, into space, and suddenly roundness is everywhere. That's weird, right? Nature on Earth seems to love variety, but nature in space seems obsessed with spheres. The answer to this mystery is going to take us on a journey through gravity, energy, rotation, and some absolutely mind-blowing physics. And here's the thing that really gets me excited about this topic. The reason things are round in space is the same reason water finds its level, the same reason soap bubbles are spherical, the same reason a spinning pizza dough spreads out into a disc. It's all connected, and by the end of this video, you're going to see the universe in a completely different way. So let's start with the most important concept we need to understand. Gravity. And I know everyone knows what gravity is. Things fall down. But gravity is so much weirder and more interesting than just things fall down. Gravity is the reason we're having this conversation at all. Gravity is a force that attracts all matter to all other matter. Every single particle in the universe is pulling on every other particle in the universe. Right now, you are gravitationally attracted to your phone, to the person sitting next to you, to the building you're in, and yes, technically, to every star in every galaxy in the observable universe. Now, most of these forces are so incredibly tiny that we never notice them. The gravitational pull between you and your phone is utterly negligible. But here's the thing, gravity never stops, it never turns off, and it adds up. When you get enough mass together in one place, gravity starts to become significant. And this is where our story really begins. Imagine you're floating in space and you've got a big cloud of gas and dust. This is how everything starts, by the way. Stars, planets, solar systems, they all begin as clouds of gas and dust floating in space. Now this cloud is huge. We're talking light years across, and it's just sitting there very slowly drifting around. But here's the thing, this cloud isn't perfectly uniform. Some regions have slightly more gas than others, just random variations. And in those denser regions, gravity is slightly stronger. So those denser regions start to pull in more gas from the surrounding areas, which makes them denser, which makes their gravity stronger, which pulls in more gas. You see where this is going? This is what we call gravitational collapse, and it's one of the most important processes in the entire universe. This is how stars form. This is how planets form. This is how galaxies form. Everything big in the universe exists because gravity pulled stuff together. And this brings us to the key insight that's going to unlock this whole mystery. When gravity pulls things together, it pulls them toward the center of mass. Think about it. You've got this cloud of gas, and every particle in that cloud is being pulled toward every other particle. But the net effect, the overall result, is that everything gets pulled toward the center. The center is where the most mass is. It's where all those gravitational vectors, all those pulls from all those different directions, balance out. So everything wants to fall toward the center. Now here's where it gets interesting. Imagine you've got two particles of gas on opposite sides of this collapsing cloud. They're both falling toward the center, but they're falling from opposite directions. So they're falling toward each other. And as this cloud collapses, every particle is basically falling toward every other particle, and they're all falling toward this common center point. What shape do you think you get when everything is being pulled equally toward a single center point from all directions? A sphere. It has to be a sphere, because a sphere is the only shape where every point on the surface is the same distance from the center. If the collapsing cloud formed into any other shape, like a cube or a pyramid or an irregular blob, then some parts of the surface would be closer to the center than others. And gravity doesn't like that. See, gravity is always trying to minimize something called gravitational potential energy. This is the energy that objects have by virtue of being far from each other. The farther apart two masses are, the more gravitational potential energy they have. And in physics, systems always try to minimize their energy if they can. It's like how water flows downhill. Water at the top of a hill has more gravitational potential energy than water at the bottom. And if you give it a chance, that water is going to flow down and minimize its energy. Same thing happens with our cloud of gas. All those particles want to get as close to each other as possible because that minimizes the total gravitational potential energy of the system. And the shape that lets every particle get as close as possible to every other particle on average is a sphere, not a cube, not a cylinder, a sphere. This is why soap bubbles are round, by the way. Surface tension is trying to minimize the surface area for a given volume, and a sphere has the minimum surface area for any given volume. It's the same principle, just a different force. So gravity naturally creates spheres. That's the fundamental answer to our question. But of course, reality is more complicated than that. Because not everything in the universe is a perfect sphere. And that's where things get really interesting. Let's talk about rotation. Because almost nothing in the universe is actually standing still. Everything is spinning. The Earth is spinning. The Sun is spinning. Galaxies are spinning. Even black holes spin. And rotation changes everything. To understand why, we need to talk about centrifugal force. Now, technically, centrifugal force isn't a real force. It's what we call a fictitious force or a pseudo-force. It's an apparent force that you feel when you're in a rotating reference frame. But you know what? It feels real enough when you're experiencing it. If you've ever been on a merry-go-round or taken a sharp turn in a car, you've felt centrifugal force. It's that feeling of being pushed outward, away from the center of rotation. Here's what's actually happening. When something is rotating, it wants to move in a straight line because of inertia. Newton's first law: an object in motion stays in motion in a straight line unless acted upon by a force. But if you're on a rotating platform, you're constantly being pulled toward the center to keep you moving in a circle. From your perspective, though, it feels like there's a force pushing you outward. That's centrifugal force. Now apply this to a planet. A planet is spinning, right? So everything on the surface of that planet is experiencing centrifugal force. And where is that force strongest? At the equator. Because the equator is the farthest point from the axis of rotation. If you're standing at the North Pole, you're basically standing on the axis of rotation. You're just spinning in place. But if you're standing on the equator, you're being whipped around at over 1,000 miles per hour in the case of Earth. This centrifugal force is pushing outward at the equator, working against gravity. And the result is that planets bulge out at the equator. They're not perfect spheres. They're what we call oblate spheroids. They're slightly squashed at the poles and bulged out at the equator. Earth is about 27 miles wider at the equator than it is from pole to pole. That's not much compared to Earth's total diameter of about 8,000 miles, but it's measurable. And some planets are way more squashed than Earth. Jupiter, for example, spins really fast. A day on Jupiter is only about 10 hours long, and Jupiter is huge and made mostly of gas, so it's easier to deform. The result is that Jupiter is visibly oblate. You can see it in pictures. It's noticeably fatter at the equator than it is from pole to pole. Jupiter's equatorial diameter is about 7,000 miles larger than its polar diameter. That's a significant bulge. Saturn is even more extreme. Saturn spins fast and is also a gas giant, and its equatorial diameter is about 7,500 miles larger than its polar diameter. You can really see that flattening in images of Saturn. It looks like someone sat on it. So rotation fights against gravity's desire to make everything perfectly spherical. Gravity wants to pull everything into a sphere. Rotation wants to fling everything outward at the equator. The final shape is a compromise between these two forces, and the faster something spins, the more it bulges. This is true for everything from planets to stars to entire galaxies. And this brings us to another interesting point. Not everything in the universe is round. Asteroids, for example, small moons. These things are often very irregular shaped. They look like potatoes or peanuts or lumpy rocks. Why? Because they're too small. Remember, gravity is what makes things round, but gravity is a weak force. It takes a lot of mass to make gravity strong enough to crush rock and iron into a spherical shape. When an object is small, The gravity pulling everything toward the center isn't strong enough to overcome the structural strength of the rock itself. Rock is actually pretty strong on small scales. It can support itself against gravity. So small objects can maintain irregular shapes. They don't have enough gravity to squeeze themselves into spheres. But there's a threshold. Once an object gets big enough, once it has enough mass, gravity becomes strong enough to overcome the structural strength of rock. The object literally crushes itself into a spherical shape. Any big lumps or bumps or irregular features get pulled down toward the center. The rock itself flows almost like a very, very slow liquid until the object reaches a roughly spherical shape. This threshold is called the limit of hydrostatic equilibrium, and it's one of the official criteria for something to be classified as a planet rather than an asteroid or dwarf planet. To be a planet, an object has to be big enough that its gravity is strong enough to pull it into a roughly spherical shape. For rocky objects, this threshold is somewhere around 300 to 600 miles in diameter, depending on the composition and other factors. Below that size, you get asteroids and small moons with irregular shapes. Above that size, gravity wins, and you get spheres. Well, oblate spheroids if they're spinning, but you get the idea. This is why Ceres, the largest object in the asteroid belt, is round. It's big enough that its gravity pulled it into a sphere. Same with Pluto. Pluto might have been demoted from planet status, but it's definitely round because it's big enough. Now let's talk about stars, because stars are even more interesting. Stars are round for the same basic reason that planets are round, gravity. But stars have an additional complication. They're hot. Really hot. The sun's surface is about 10,000 degrees Fahrenheit, and the core is about 27 million degrees. And heat creates pressure. When you heat a gas, the molecules move faster. And when molecules move faster, they collide with each other harder and more often. This creates pressure. The hotter the gas, the more pressure. And in a star, this heat and pressure is trying to make the star expand. It's pushing outward. But gravity is pulling everything inward. So a star is in a constant battle between gravity trying to crush it and pressure trying to blow it apart. The result is what we call hydrostatic equilibrium. Hydro meaning fluid, static meaning not moving, equilibrium meaning balance. The star reaches a balance where the inward pull of gravity exactly equals the outward push of pressure at every point. And what shape naturally arises from this balance? A sphere. Again, it's because a sphere is the shape where every point on the surface is the same distance from the center. If a star were any other shape, say a cube, then the corners would be farther from the center than the faces. Gravity would be weaker at the corners and stronger at the faces. But the pressure would be the same everywhere because the temperature and density would try to even out. So the faces would get pushed out by pressure, and the corners would get pulled in by gravity, and you'd end up with a sphere. The only stable shape for something in hydrostatic equilibrium is a sphere. Now, stars also rotate, just like planets. So stars are also oblate spheroids bulging at the equator. But most stars don't spin very fast, so they're pretty close to perfect spheres. The Sun, for example, rotates about once every 25 days at the equator. That's pretty slow. So the Sun is only very slightly oblate. You can't see the difference with your eyes. But some stars spin much faster. Young stars especially can spin very rapidly, and when they do, they can become quite flattened. There are stars known as B stars that spin so fast they're visibly oblate, and they sometimes throw off material at their equators because the centrifugal force is so strong. These stars can spin at speeds of over 1 million miles per hour at the equator. At those speeds, the star is barely holding itself together against the centrifugal force trying to tear it apart. And then there are stellar remnants like neutron stars and white dwarfs. Neutron stars are the collapsed cores of massive stars after they explode as supernovae. They're incredibly dense. A neutron star packs more mass than the Sun into a sphere only about 12 miles across. And they spin fast, really fast. Some neutron stars rotate hundreds of times per second. These are called pulsars, and they're some of the most extreme objects in the universe. At these rotation rate, the centrifugal force is enormous. A pulsar can be spinning so fast that the equator is moving at a significant fraction of the speed of light. The result is that pulsars are very oblate. Some of them are 20% wider at the equator than they are from pole to pole. That's a huge deformation, and yet they're still basically round. Oblate spheroids are still a type of round. Now let's zoom out and talk about something even bigger. Galaxies. Galaxies are huge collections of stars, gas, dust, and dark matter all held together by gravity. And galaxies come in different shapes. Some are spherical or elliptical. Some are irregular and blobby. But the most iconic galaxies, the ones everyone thinks of when they hear the word galaxy, are spiral galaxies. And spiral galaxies are flat disks. Why? Same reason, rotation. Galaxies rotate, they're spinning. And when a big cloud of gas and stars is rotating, centrifugal force flattens it out into a disk. But wait, why a disk and not just an oblate spheroid like a planet? The difference is that planets are solid, or at least relatively cohesive. The material is all stuck together. But a galaxy is mostly empty space. The stars and gas in a galaxy are separate objects orbiting around a common center of mass. They're not physically connected to each other. When you have a cloud of particles all orbiting around a common center, and those particles can collide with each other and exchange momentum, they naturally settle into a flat disk. Here's why. Imagine all these particles are orbiting in random directions. Some are going clockwise, some are going counterclockwise, some are going at weird angles. Over time, these particles collide with each other. And when they collide, they average out their motion. If one particle is going up and another is going down and they collide, their vertical motions cancel out, but their horizontal motions add together. Do this over and over again with billions and trillions of particles over millions and billions of years, and all the random vertical motion gets cancelled out. All that's left is the net rotation. And all that net rotation is in one plane, the plane of the disk. This is why Saturn's rings are flat. It's why the solar system is mostly flat. All the planets orbit the Sun in roughly the same plane. It's why galaxies are flat. It's a natural consequence of rotation and collisions in a gravitating system. We call this process dynamical relaxation or collisional damping, and it's a fundamental process in astrophysics. But not all galaxies are disks. Elliptical galaxies are spherical or ellipsoidal. Why? Because they don't have much rotation. Elliptical galaxies are formed mostly from galaxy mergers. When two galaxies collide and merge, their organized rotation gets disrupted. The result is a big blob of stars moving in random directions with no net rotation. And without rotation, there's no force to flatten the galaxy into a disk. Gravity just pulls everything into a rough sphere or ellipsoid. So the shape of a galaxy depends on whether it's rotating in an organized way or whether the stars are moving in random directions. Rotation creates disks. Random motion creates spheres or ellipsoids. It's all about the balance between ordered and disordered motion. Now let's talk about something really weird, black holes. Black holes are round. Well, sort of. Black holes don't really have a surface. What they have is an event horizon, which is the boundary beyond which nothing, not even light, can escape. And that event horizon is spherical. Or actually, for a rotating black hole, it's an oblate spheroid. Sensing a pattern here? Non-rotating black holes, which we call Schwarzschild black holes after the physicist who first solved Einstein's equations for them, have perfectly spherical event horizons. This makes sense because a black hole is the ultimate expression of gravity. All the mass is concentrated at a single point in the center, the singularity. And gravity pulls equally in all directions from that point. So the event horizon, which is determined by the strength of gravity, is spherical. Rotating black holes, which we call Kerr black holes after the physicist who solved those equations, have oblate spheroidal event horizons. And they have an additional structure called the ergosphere, which is a region outside the event horizon where space-time itself is dragged around by the rotation of the black hole. This is called frame dragging, and it's one of the weirder predictions of general relativity. But even with all this weirdness, the basic shape is still round. The rotation just flattens it a bit at the poles. And here's something really cool. There's a limit to how fast a black hole can spin. If a black hole spins too fast, the centrifugal force at the equator becomes so strong that the event horizon would disappear and the singularity would be exposed. We call this a naked singularity. and it's generally believed that naked singularities can't exist in nature. This is called the cosmic censorship hypothesis. Nature doesn't allow singularities to be naked. They must always be hidden behind an event horizon. So there's a maximum spin rate for a black hole, and at that maximum spin rate, the black hole is very oblate but still roughly round. The event horizon is more like a squashed sphere than a sphere, but it's still fundamentally a closed surface surrounding the singularity. Let's talk about moons for a bit, because moons are fascinating and they show us the full range of shapes we've been discussing. Large moons are round. Earth's moon is round. Jupiter's big moons like Ganymede and Callisto are round. Saturn's moon Titan is round. These moons are big enough that gravity pulled them into spheres when they formed, but small moons are weird-shaped. Mars's moons, Phobos and Deimos, look like potatoes. Some of Saturn's smaller moons look like ravioli or flying saucers. There are moons that look like sponges or walnuts. These small moons are basically captured asteroids or debris from collisions, and they're too small for gravity to round them out. And then there are some moons that are in between. Moons that are big enough that gravity tried to make them round, but other forces interfered. One of the most interesting examples is Saturn's moon Iapetus. Iapetus is round, but it has this bizarre equatorial ridge that goes almost all the way around the moon. It looks like someone glued a walnut shell around the equator. Nobody is quite sure how this ridge formed, but it's probably related to Iapetus's rotation and maybe some ancient geological activity. Another weird moon is Haumea, which orbits out past Pluto in the Kuiper Belt. Haumea is round, technically. It's big enough that it qualifies as a dwarf planet. But Haumea spins incredibly fast. A day on Haumea is only 4 hours long, and Haumea is mostly made of rock and ice, which can't withstand that kind of centrifugal force. So Haumea has been stretched out into an ellipsoid. It's shaped like a football or a rugby ball. It's about twice as long as it is wide. Haumea is so deformed that it doesn't even really look round anymore. It's round in cross-section, but viewed from the side, it's clearly elongated. This shows us that there are limits to how round things can be. If something spins fast enough, centrifugal force can overcome gravity and deform the object significantly. The faster the spin, the more deformation. This is true for everything from moons to stars. Now let's talk about what happens when things collide, because collisions are a major part of how celestial objects form and evolve. When two objects collide in space, the result depends on their sizes and velocities. Small, slow collisions might just create craters or transfer some material from one object to the other, but big, fast collisions can completely reshape objects. The Moon, Earth's moon, is thought to have formed from a giant impact. About 4.5 billion years ago, a Mars-sized object crashed into the early Earth. The collision was so energetic that it vaporized both the impactor and a large chunk of Earth's mantle. This vaporized material was thrown into orbit around Earth, where it cooled and condensed and eventually came together to form the Moon. This kind of collision is so violent that any shape the objects had before is completely destroyed. Everything is melted and vaporized and mixed together, and then gravity takes over. As the material cools and comes together, gravity pulls it into a sphere. So even though the Moon was born from violence and chaos, it ended up round because gravity always wins in the end. This is true for most large celestial objects. They might have formed from collisions, from gradual accumulation of material, from the collapse of gas clouds, or from other processes. But regardless of how they formed, if they're big enough, gravity pulls them into spheres. The process might take millions or billions of years, but the end result is always the same, round. And this brings us to a deeper point about why roundness is so common in the universe. It's because roundness is a low-energy state. It's a stable configuration. In physics, systems naturally evolve toward lower energy states if they can. A ball at the top of a hill will roll down to the bottom of the valley. Water will flow downhill to the lowest point. And matter will arrange itself into spheres because that minimizes gravitational potential energy. This is a fundamental principle in physics called the principle of least action, or the principle of minimum energy. Systems evolve to minimize their energy or their action. And for gravitating systems, the minimum energy configuration is a sphere. So spheres are everywhere in the universe, not because there's some cosmic sphere-making machine, but because spheres are the natural, stable, minimum energy state for matter under the influence of gravity. Now I want to talk about something that might seem unrelated, but is actually deeply connected to all of this. Soap bubbles. I mentioned soap bubbles earlier, and I said they're round because surface tension tries to minimize surface area. But let's dig into that a bit more, because it illustrates the same principle we've been talking about. A soap bubble is a thin film of soap surrounding a volume of air. The soap film has surface tension, which is a property of liquids, where the surface acts like a stretched elastic membrane. Surface tension arises because the molecules in the liquid are attracted to each other. Molecules in the bulk of the liquid are surrounded by other molecules on all sides, so the forces balance out. But molecules at the surface have neighbors only on one side. They're pulled inward by the molecules below them, and this creates tension in the surface. Surface tension wants to minimize the surface area, because having more surface area means having more molecules in this high-energy surface state. And systems want to minimize energy. So the soap film tries to contract to minimize its surface area. But the air inside the bubble is pushing outward, creating pressure. The bubble reaches a balance where the inward pull of surface tension equals the outward push of air pressure. And what shape minimizes surface area for a given volume? A sphere. This is exactly analogous to how stars work. In a star, gravity is like the surface tension pulling inward, and pressure from the hot gas is pushing outward. The star reaches hydrostatic equilibrium, and the stable shape is a sphere. It's the same mathematics, just different forces. Or think about water drops. Small water drops in free fall are spherical because of surface tension. Water is always trying to minimize its surface area because of the surface energy. Again, the minimum surface area for a given volume is a sphere. So water drops are round for the same reason soap bubbles are round, and for fundamentally the same reason planets are round. It's all about minimizing energy. And this gets at something really profound. The laws of physics are universal. The same principles that determine the shape of a soap bubble also determine the shape of a planet or a star or a galaxy. Gravity, pressure, surface tension, these are all just forces. And the mathematics that describes how objects respond to forces is the same whether we're talking about a millimeter-sized water drop or a billion-mile-wide star. This is one of the most beautiful things about physics. The universe doesn't have different rules for different situations. The same fundamental laws apply everywhere, from the smallest scales to the largest. And those laws tend to create similar patterns and structures. Spheres are common in the universe because spheres are what you get when you minimize energy in a symmetric situation. Let's talk about some exceptions and edge cases, because not everything fits neatly into this round paradigm. Comets, for example. Comets are often irregularly shaped. They're like asteroids, too small for gravity to round them out. But comets are interesting because they're made mostly of ice, and ice behaves differently than rock. Ice is weaker and more volatile. When a comet gets close to the sun, the ice starts to vaporize, creating the characteristic tail. This process can erode the comet's surface in uneven ways, creating irregular shapes. Some comets are shaped like peanuts or dumbbells, possibly because they're two objects that came together gently and stuck without fully merging. The famous comet 67P Churyumov-Gerasimenko, which the Rosetta spacecraft visited, is shaped like a rubber ducky. It's clearly two lobes connected by a neck. These irregular shapes tell us about the comet's history. They tell us that the comet never got hot enough or had enough internal pressure to flow and round itself out. It's been cold and solid for its entire existence. It's a frozen relic from the early solar system, preserved in its original irregular shape. Asteroids are similar. Most asteroids are irregularly shaped. But the interesting thing is that some asteroids are clearly fragments from larger objects that broke apart in collisions. They have angular shapes with sharp edges and flat faces. These asteroids are literally pieces of broken planets or broken protoplanets. And their irregular shapes are evidence of violent collisions in the asteroid belt's history. But there are also some asteroids that are more rounded. These are probably intact planetesimals, small planetary building blocks that never got incorporated into a larger planet. Or they're asteroids that got partially melted at some point, maybe from radioactive decay in their interiors. And the melting allowed gravity to start pulling them into more spherical shapes before they cooled and solidified again. So asteroid shapes can tell us a lot about their history. Are they fragments or intact bodies? Have they been heated, or have they always been cold? Have they been involved in collisions? The shape is a clue to the story. Now let's talk about really extreme environments. What happens to shapes in the most intense gravitational fields in the universe? Near a black hole, gravity is so strong that it warps space-time itself. Light doesn't travel in straight lines near a black hole. Light bends and curves following the curvature of space-time. If you were to fall toward a black hole, you'd experience something called spaghettification. The gravity gradient would be so strong that the tidal forces would stretch you out like a noodle. Your feet would be pulled much harder than your head if you were falling feet first, because your feet would be closer to the black hole. This tidal stretching would literally tear you apart. But even in this extreme environment, roundness persists. The event horizon is still round. The accretion disk of material falling into the black hole is flat because of rotation, but it's circular when viewed from above. Even the shadows of black holes, which we've now actually imaged thanks to the Event Horizon Telescope, are round. The famous image of the black hole at the center of galaxy M87 shows a bright ring surrounding a dark shadow. That shadow is the black hole's event horizon, and it's round. This roundness in the shadow isn't just because the event horizon is round, it's also because of an effect called gravitational lensing. The black hole's gravity bends light around it, creating multiple images and a bright ring called the photon sphere. This is the region where light can actually orbit the black hole. And this photon sphere is, you guessed it, spherical. So even in the most extreme gravitational environments, where space-time itself is twisted and bent, roundness emerges. It's a testament to the fundamental symmetry of gravity. Gravity acts equally in all directions from a point mass, and equal action in all directions naturally creates spherical symmetry. Let's talk about the very early universe, because the story of roundness goes all the way back to the Big Bang. In the first moments after the Big Bang, the universe was incredibly hot and dense. It was so hot that matter couldn't exist in any form we would recognize. There were no atoms, no molecules, not even protons or neutrons. Just a soup of fundamental particles and energy. But even in this primordial soup, gravity was already at work. And there were tiny variations in density, quantum fluctuations that got amplified as the universe expanded. These density variations were the seeds that would eventually grow into galaxies and clusters of galaxies. And what shape were these primordial density fluctuations? They were roughly spherical because they were created by random quantum fluctuations that had no preferred direction. As the universe expanded and cooled, these density fluctuations grew. Gravity amplified them. Denser regions attracted more matter, becoming denser still. Eventually, these regions became gravitationally bound. They stopped expanding with the rest of the universe and started collapsing under their own gravity. And as they collapsed, they formed the first stars and galaxies. So the roundness we see in the universe today has its origins in the very first moments after the Big Bang. The seeds were planted then, and gravity has been shaping them into spheres ever since. It's a process that's been going on for nearly 14 billion years, and it's still going on today. Let's talk about human-made objects in space, because they're an interesting contrast. Satellites and space stations are not round. They're all angles and solar panels and antennas. Why? Because we design them for function, not minimum energy. A round satellite would be more stable in some sense, but it would be harder to pack instruments into and harder to attach things to. But there's an interesting thing that happens to human-made objects over long time scales in space. They get eroded by micrometeoroids and radiation. Over millions of years, if a satellite were left in space, these tiny impacts would gradually smooth out its surface. Sharp corners would get blunted. Flat surfaces would get pitted and roughened. Eventually, over geological timescales, even a human-made object would start to look more round just from random erosion. Of course, long before that happened, The object would probably be broken apart by larger impacts or fall out of orbit, but it's an interesting thought experiment. Nature has a way of rounding things off, given enough time. Now let's think about what happens at very small scales. Atoms aren't round in the classical sense. They're quantum objects, and they don't really have defined shapes. But atomic nuclei are approximately spherical. Why? Same reason. The nuclear force, which holds protons and neutrons together in the nucleus, acts equally in all directions. So nuclei tend to be spherical. There are exceptions. Some nuclei are deformed. They're prolate, shaped like a football, or oblate, shaped like a pancake. This happens when the nucleus has a certain configuration of protons and neutrons that favors a non-spherical shape. It's similar to how a rotating planet is oblate. The nucleus might be spinning, or it might just be that the quantum mechanical configuration of nucleons favors a deformed shape. But most nuclei are approximately spherical. And this spherical symmetry is important because it affects how nuclei interact with each other and with radiation. Nuclear physics would be much more complicated if nuclei had random, irregular shapes. Even elementary particles like electrons are point-like as far as we can tell. They have no measurable size or shape. But the probability distributions that describe where an electron is likely to be found around an atom, the electron orbitals, often have spherical symmetry. The simplest orbital, the 1s orbital, is perfectly spherical. More complex orbitals have more complex shapes, but they still have a lot of symmetry. So this theme of roundness and spherical symmetry runs through physics from the largest scales to the smallest. It's a consequence of the fundamental symmetries in the laws of nature. When a force acts equally in all directions, you get spherical symmetry. And many of the forces in nature, like gravity and the Coulomb force between electric charges, do act equally in all directions. Let's talk about the future. What will happen to all these round objects over cosmic timescales? Stars will die. Small stars like the Sun will swell into red giants and then shed their outer layers, leaving behind white dwarfs. White dwarfs are round, dense spheres of carbon and oxygen supported by quantum mechanical pressure. They'll cool slowly over trillions of years, eventually becoming black dwarfs, cold dark spheres floating in space. Massive stars will explode as supernovae, leaving behind neutron stars or black holes. Both are round. Neutron stars are oblate if they spin fast, but they're still round. Black holes are definitely round, or at least their event horizons are. Galaxies will collide and merge. When the Milky Way and Andromeda galaxies collide in about 4 billion years, they'll merge into a larger elliptical galaxy. That galaxy will be round, more or less. It might not be a flat disk anymore because the collision will disrupt the organized rotation, but it'll be a three-dimensional ellipsoid. On even longer timescales, trillions of years in the future, the universe will become a very different place. Stars will stop forming because all the gas will be locked up in stars or stellar remnants or black holes. Galaxies will fade as their stars die. Black holes will evaporate through Hawking radiation, a quantum mechanical process that causes black holes to slowly lose mass by radiating particles. Eventually, the universe will continue be filled with nothing but cold, dead stellar remnants, black holes that haven't evaporated yet, and diffuse radiation. And even those black holes will eventually evaporate. A black hole with the mass of the Sun would take about 10 to the 67 years to evaporate. A supermassive black hole with 1 billion solar masses would take about 10 to the 100 years. These are timescales that are almost impossible to comprehend. The current age of the universe, 14 billion years, is nothing compared to these numbers. But even as black holes evaporate, they remain round until the very end. The event horizon shrinks as the black hole loses mass, but it stays spherical. Right up until the final moment when the black hole evaporates completely in a final burst of radiation, it's round. Roundness persists to the very end. And what about the radiation that fills the universe after everything has evaporated? Radiation doesn't have a shape in the same way that matter does. But radiation does have intensity patterns and distributions. And interestingly, the cosmic microwave background radiation, the afterglow of the Big Bang, is almost perfectly uniform in all directions. It's spherically symmetric to an incredibly high degree, with variations of only 1 part in 100,000. This uniformity tells us that the early universe was extremely smooth and symmetric, and it's another example of how nature tends towards symmetry and uniformity when left to its own devices. The universe started in a hot, dense, symmetric state, and even though it's evolved into a complex place with stars and galaxies and planets, that underlying symmetry is still there in the background radiation. Let's think about artificial gravity for a moment because it relates to rotation and roundness. On Earth, we feel gravity pulling us down because we're standing on a massive planet. But in space, in freefall, there's no up or down. Everything is weightless. If you want to create artificial gravity in a spacecraft, one way to do it is to spin the spacecraft. This is a common trope in science fiction. A rotating space station or spacecraft creates centrifugal force that pushes people toward the outer rim. If you're standing on the inside of a rotating cylinder, you feel like there's gravity pulling you toward the floor. The faster the rotation, the stronger the apparent gravity. And what shape makes sense for a rotating space station? A cylinder or a torus, a donut shape. These are round in cross-section. You could theoretically have a rectangular rotating space station, but it would be structurally inefficient. The corners would experience different forces than the flat sides. A round cross-section distributes the structural stress evenly. The famous Stanford torus design for a space station is literally a giant rotating torus, a donut about a mile in diameter. People would live on the inside surface of the torus, and the rotation would create artificial gravity. And this design is round because roundness is the most efficient and stable shape for a rotating structure. So even in our future as a spacefaring civilization, if we build large structures in space, they'll probably be round. Not because we're imitating nature, but because the same physical principles that make planets round also make rotating space stations round. Let's talk about density and how it affects shape. I mentioned earlier that small objects can maintain irregular shapes because their gravity isn't strong enough to overcome the structural strength of rock. But there's more to it than just size. Density matters too. An object made of solid iron can maintain an irregular shape at larger sizes than an object made of ice or fluffy dust. This is because gravity depends on mass, not volume. A dense object has more mass for its size, so it has stronger gravity. And stronger gravity means it's more likely to pull itself into a round shape. This is why metallic asteroids tend to be more irregular than rocky asteroids of the same size. Metal is stronger and can support itself against gravity better than rock. But it also means that if you have an object made of something very weak and fluffy, like a loosely packed dust cloud, it'll collapse into a sphere at much smaller sizes. This is exactly what happens when stars form. A cloud of gas and dust is so diffuse and weak that gravity easily collapses it into a sphere, even though the total mass might not be that large by astronomical standards. Comet 67P, the rubber ducky-shaped comet I mentioned earlier, is interesting in this regard. It's made of ice and dust, which is relatively weak material. And yet it's not round. Why? Because it's small enough that gravity is weak, and it's probably made of two objects that came together very gently and just stuck. The collision wasn't energetic enough to melt or deform the material, so the two lobes retained their shapes. But if you took Comet 67P and heated it up, melted the ice, and let it refreeze, it would collapse into a more spherical shape. The liquid phase would allow gravity to pull everything toward the center. This is essentially what happens inside large planets. The interior is hot enough that the rock can flow very slowly, and gravity can pull the planet into a sphere. Earth's interior is not liquid in the sense of being a liquid ocean, but it's hot enough that the rock can flow like a very thick fluid over geological timescales. This is why Earth is round. The interior is plastic enough that gravity can shape it. If Earth were cold all the way through, solid and rigid, it might not be perfectly round. There might be mountains that stuck up higher than gravity could pull down. But Earth has been hot enough throughout its history that gravity has been able to shape it into a sphere. This also explains why the Moon is round even though it's smaller than some of the features we observe in the solar system. The Moon formed hot. It was probably entirely molten when it first formed from the debris of that giant impact. And when it cooled, Gravity had already shaped it into a sphere. So even though the moon is now cold and solid, it's still round because it was shaped when it was molten. Let's talk about tidal forces in more detail because they're a fascinating exception to the rule of roundness. Tidal forces arise when gravity varies across an object. The classic example is Earth's oceans. The moon's gravity pulls on Earth, but it pulls slightly harder on the side of Earth facing the moon than on the center of Earth, and it pulls slightly less hard on the far side. This difference in gravitational pull across Earth's diameter creates tidal forces. These forces try to stretch Earth along the line connecting Earth and the moon. The result is that Earth's oceans bulge out toward the moon and also bulge out on the opposite side. These bulges are the ocean tides. As Earth rotates under these bulges, we experience high and low tides. Now, Earth itself is also deformed by tidal forces, not just the oceans. The solid Earth bulges by about a foot in response to the moon's tidal forces. You can't feel this because you're on the surface moving with the bulge, but it's measurable. And this tidal deformation is slowly changing Earth's rotation. Tidal forces transfer angular momentum between Earth's rotation and the moon's orbit. Earth's rotation is slowing down, and the moon is gradually moving farther away. Billions of years ago, the moon was much closer to Earth, and Earth rotated much faster. A day was only a few hours long. The moon has been gradually moving away, and Earth's rotation has been gradually slowing because of tidal forces. Eventually, billions of years in the future, Earth will become tidally locked to the moon. This means Earth's rotation period will equal the moon's orbital period. The same side of Earth will always face the moon, just like the same side of the moon always faces Earth. When this happens, the tidal bulges will be locked in place, no longer moving, and the tidal forces will stop transferring angular momentum. But here's the interesting thing. Even with tidal locking, Earth will still be round. It'll be slightly elongated along the Earth-Moon line because of the permanent tidal bulge, but it'll still be basically round. The tidal deformation is a small perturbation on top of the basic spherical shape determined by gravity. Many moons in the solar system are tidally locked to their planets. Our moon is tidally locked to Earth. Jupiter's big moons are tidally locked to Jupiter. Saturn's moons are tidally locked to Saturn, and these moons are all round, or at least mostly round. Some of them are slightly elongated toward their planet because of tidal forces, but the basic shape is still spherical. There's one more aspect of tides that's really fascinating: tidal disruption. If an object gets too close to a massive body, tidal forces can literally tear it apart. There's a distance called the Roche limit, named after the French astronomer who calculated it. Inside the Roche limit, tidal forces are stronger than the object's own gravity, and the object gets ripped apart. Saturn's rings are probably debris from moons that got too close to Saturn and were torn apart by tidal forces. Or they might be material that never coalesced into a moon in the first place because it was inside the Roche limit. Either way, the rings exist because tidal forces prevented material from coming together into round moons. And this happens on much more dramatic scales too. When a star gets too close to a black hole, it can be tidally disrupted. The side of the star facing the black hole is pulled much harder than the far side, and the star gets stretched like taffy. Eventually, the star is torn apart and the debris forms an accretion disk around the black hole. Astronomers have observed these tidal disruption events. They're incredibly luminous because the stellar material heats up as it falls into the black hole. So tidal forces are one of the main ways that round objects can be deformed or destroyed. But notice that the end result is still orderly. The debris doesn't just fly off in random directions. It forms an accretion disk, which is round when viewed from above. Even in destruction, roundness emerges. Let's talk about ring systems more, because they're such a beautiful example of how rotation creates flat, round structures. Saturn is famous for its rings, but all the giant planets have rings. Jupiter has faint rings. Uranus has rings. Neptune has rings. Even some asteroids have been found to have rings. Ring systems form when material is in orbit around a planet or other body within the Roche limit. The material can't coalesce into a moon because tidal forces would tear it apart. But the material can orbit stably. And over time, collisions between particles in the ring cause them to settle into a thin, flat disk. This is the same process that flattens galaxies and protoplanetary disks. What's amazing about Saturn's rings is how thin they are. The rings extend hundreds of thousands of miles from side to side, but they're only about 30 feet thick in most places. That's an aspect ratio that's hard to even visualize. If Saturn's rings were the size of a football field, they'd be thinner than a razor blade. This extreme flatness is the result of billions of years of collisions, damping out any vertical motion. Any particle that's moving up or down will eventually collide with another particle and lose that vertical velocity. What's left is pure circular motion in a single plane. The result is a disk so flat it almost looks two-dimensional. And the rings themselves have structure. There are gaps in the rings called divisions. The largest is the Cassini divisions, a gap several thousand miles wide between the A ring and B ring. These gaps are caused by orbital resonances with Saturn's moons. A particle in the Cassini division would orbit Saturn in exactly half the time it takes the moon Mimas to orbit. This means the particle gets a gravitational tug from Mimas at the same point in its orbit over and over again. These repeated tugs add up and eventually eject the particle from that region, creating a gap. So even within ring systems, which are already flat and round, there's additional structure created by the complex interactions between gravity and orbital mechanics. It's turtles all the way down. Roundness on top of roundness on top of roundness. Let's think about what would happen if gravity worked differently. Suppose instead of following an inverse square law, where the force decreases with the square of the distance, gravity followed a different law. Would things still be round? The answer is, it depends. If gravity were stronger at large distances, objects would clump together more easily, and you might get different structures. If gravity were weaker, objects might not clump together at all, and you wouldn't get planets or stars. But as long as gravity is radially symmetric, meaning it acts equally in all directions from a point, you'd still get spherical symmetry. The inverse square law itself comes from the fact that we live in three-dimensional space. Imagine a point mass emitting gravitational field lines in all directions. Those field lines spread out over the surface of a sphere. The area of a sphere increases with the square of the radius. So the field strength, the number of field lines per unit area, decreases with the square of the radius. That's where the inverse square law comes from. In a two-dimensional universe, you'd have an inverse linear law. In a four-dimensional universe, you'd have an inverse cube law. But in all cases, as long as the force is radially symmetric, you'd get round objects. The sphere is the natural shape for radial symmetry in any number of dimensions. This is actually a profound point. The fact that we see spheres everywhere in the universe is telling us something fundamental about the geometry of space and the nature of gravity. It's confirming that space is three-dimensional and approximately flat on large scales, and that gravity is a radial force. If the universe had weird geometry, or if gravity had weird directional properties, we wouldn't see so many spheres. Let's talk about planets in other solar systems, exoplanets. We've discovered thousands of exoplanets over the past couple of decades, and while we can't directly image most of them to see their shapes, we can be pretty confident that they're round. Why? Because they're big enough. If they're planet-sized, they're big enough that gravity pulled them into spheres. Some exoplanets are really extreme. There are hot Jupiters, gas giant planets that orbit very close to their stars. These planets are tidally locked, with one side always facing the star. And the star-facing side is incredibly hot, while the dark side is much cooler. This creates extreme temperature gradients and probably ferocious winds as the atmosphere tries to redistribute heat. You might think these extreme conditions would deform the planet, and you'd be right. Hot Jupiters are probably very oblate because of their rapid rotation and because of tidal forces from their nearby star, but they're still basically round. The deformations are perturbations on top of a fundamentally spherical shape. There are also super-Earths and mini-Neptunes, planets intermediate in size between Earth and Neptune. We don't have anything like these in our solar system, so we're not sure exactly what they're like. But they're definitely round. We know this because we can measure their sizes from transit observations, when they pass in front of their star, and the sizes are consistent with spherical planets. Some exoplanets might have been deformed by collisions or other violent events. There might be planets out there that are still cooling down from giant impacts, planets where the surface hasn't had time to settle into a perfect sphere yet. But given enough time, gravity will round them out. Roundness is the final state, the stable equilibrium. Let's talk about the practical implications of roundness. The fact that planets are round has been incredibly important for navigation and exploration throughout human history. Ancient Greek philosophers figured out that Earth was round by observing lunar eclipses and noticing that Earth's shadow on the moon was always circular. They also noticed that different stars were visible at different latitudes, which wouldn't make sense on a flat Earth. The roundness of Earth enabled the age of exploration. Navigators could use the angle of the sun or stars above the horizon to determine their latitude. They could calculate distances and plan routes based on the spherical geometry of Earth's surface. None of this would work if Earth were flat or irregularly shaped. And in the space age, the roundness of planets and moons has been crucial for orbital mechanics. When you're calculating orbits and trajectories, you can treat planets as point masses to a first approximation because they're spherical. If planets were irregular shaped, orbital mechanics would be much more complicated. You'd have to account for the non-uniform gravitational field. Actually, we do have to account for this to some degree. Earth isn't a perfect sphere, it's oblate, bulging at the equator, and this bulge creates a non-uniform gravitational field that affects satellites in orbit. The effect is called J2 perturbation, and it causes satellites to precess, meaning their orbital planes slowly rotate. GPS satellites have to account for this effect to maintain accurate positioning. But the point is that these are small corrections on top of a basically spherical shape. If Earth were shaped like a cube or a pyramid, orbital mechanics would be a nightmare. The spherical shape makes everything simpler. Let's think about life and roundness. Does the fact that planets are round affect the possibility of life? Absolutely. A round planet has a relatively uniform environment at any given latitude. Gravity points toward the center, so down is well defined everywhere on the surface. Water flows downhill to the lowest points, creating oceans and lakes. Weather patterns circulate in predictable ways because of the planet's rotation and spherical shape. If a planet were irregularly shaped, none of this would work the same way. Gravity would point in different directions on different parts of the surface. There might not be distinct poles and equators. Water might pool in weird places. Weather would be chaotic and unpredictable. It's hard to imagine complex life evolving in such an environment. So the roundness of planets isn't just an aesthetic feature. It's a functional necessity for the kind of stable, predictable environments that life needs. Life as we know it requires liquid water, and liquid water requires gravity to be consistent and predictable. Roundness provides that. There's also the question of planetary habitability and rotation. A planet needs to rotate to create day-night cycles and to drive weather patterns. But if a planet rotates too fast, it becomes very oblate and might even start to lose material from its equator. If it rotates too slowly, one side would be perpetually baked by the sun, while the other side would be frozen. Earth's rotation rate is in a sweet spot that creates comfortable day-night cycles without excessive deformation. And Earth's roundness combined with its axial tilt creates the seasons. The tilt means different parts of Earth receive more or less direct sunlight at different times of year. This creates temperature variations that drive all sorts of ecological and climatological processes. Without Earth's spherical shape and axial tilt, we wouldn't have seasons as we know them. Let's talk about measurement and how we know all this. How do we know planets are round? How do we measure their shapes? For bodies in our solar system, we can use multiple methods. We can take pictures from spacecraft and see the shapes directly. We can use radar to map the surface and measure precise distances. We can track spacecraft as they orbit and measure tiny variations in their trajectories caused by the non-uniform gravitational field, which tells us about the mass distribution inside the body. For Earth, we have incredibly precise measurements. We know Earth's equatorial radius is about 6,378 kilometers, and its polar radius is about 6,357 kilometers. That's a difference of about 21 kilometers, or about 0.3%. So Earth is very close to a perfect sphere, but measurably oblate. We also know that Earth's shape is slowly changing. The interior is still churning, driven by heat left over from Earth's formation and by radioactive decay. This churning drives plate tectonics and creates geological activity. And all this activity subtly changes Earth's shape over millions of years. Earth is not static. It's a dynamic system that's constantly evolving. For distant objects like stars and exoplanets, we can't see their shapes directly, but we can infer them from their properties. We can measure how fast a star is rotating from the Doppler shift of spectral lines. Faster rotation means more oblateness. We can measure the sizes of exoplanets from transit observations and confirm they're consistent with spherical shapes. We can even measure the oblateness of some nearby stars using interferometry, a technique that combines light from multiple telescopes to achieve higher resolution. All the evidence confirms what physics predicts. Large objects in space are round, or at least oblate spheroids. There are no giant cubes or pyramids or irregular blobs floating around in space, unless they're small enough that gravity can't round them out. Let's talk about the philosophy of all this, because there's something almost poetic about the ubiquity of spheres in the universe. The sphere is the perfect shape in many senses. It has the maximum volume for a given surface area. It has perfect symmetry. Every point on the surface is equivalent to every other point. There are no edges, no corners, no special directions. Ancient philosophers like Plato thought spheres were the most perfect shape and associated them with the heavens and the divine. They thought celestial objects must be spherical because spheres were perfect and the heavens were perfect. They were right that celestial objects are spherical, but they had the reasoning backwards. Celestial objects aren't spherical because spheres are perfect. They're spherical because gravity creates spheres. But maybe there's something to the Platonic idea after all. Maybe there is something fundamentally perfect about spheres, not in a mystical sense, but in a physical sense. Spheres represent the minimum energy state. They represent equilibrium and stability. They represent the natural end point of gravitational collapse. In a universe governed by simple, symmetric laws of physics, spheres are inevitable. And isn't there something beautiful about that? The same simple principle, gravity acting equally in all directions, creates spheres from the smallest asteroids to the largest stars. The mathematics is elegant. The result is universal. Everywhere we look in the universe, we see the same patterns repeating. It's a kind of cosmic harmony. Let's talk about what happens in zero-gravity environments because it's an interesting contrast. On the International Space Station in orbit around Earth, astronauts experience microgravity. Things float, there's no up or down. And in this environment, liquids behave in fascinating ways. Water doesn't pour or flow, it forms into floating blobs. And what shape do those blobs take? Spheres. Because surface tension pulls the water into a sphere to minimize surface area, just like soap bubbles. So even in zero gravity, even without the force of gravity shaping things, we still get spheres, just from a different mechanism, surface tension instead of gravity. But the underlying principle is the same, minimizing energy. Surface tension wants to minimize surface area, which means forming a sphere. Gravity wants to minimize gravitational potential energy, which means forming a sphere. Different forces, same result. This is a beautiful example of convergent solutions in nature. When different physical systems face similar constraints, they evolve towards similar solutions. Spheres are the solution to many different optimization problems in physics. Let's think about artificial planets or megastructures. If humanity ever builds really large structures in space, what shape should they be? A lot of science fiction features Dyson spheres, hypothetical megastructures that completely surround a star to capture all its energy. The name suggests a spherical shell around the star. But would that actually be stable? Actually, no. A rigid spherical shell around a star wouldn't be gravitationally stable. Any slight perturbation would cause the shell to drift toward the star on one side, and the instability would grow. This is a well-known problem in physics. You need some other force to stabilize the structure, like electromagnetic forces or active station keeping with thrusters. A more plausible megastructure might be a Dyson swarm, a huge collection of individual satellites orbiting the star and collecting its energy. These satellites would naturally arrange themselves in orbits, forming a spherical distribution around the star, not a solid sphere, but a swarm of objects in spherical symmetry. And again, we get roundness emerging from the physics of orbits and gravity. Or consider an O'Neill cylinder, a proposed space habitat shaped like a rotating cylinder. The cylinder would be several miles in diameter and tens of miles long. People would live on the inside surface, and rotation would provide artificial gravity. The cylinder isn't spherical, but its cross-section is circular. And that's for the same reasons we've been discussing: uniform distribution of stress, efficiency of structure, and the mechanics of rotation. So even our future artificial habitats in space will probably involve a lot of round shapes. Not because we're imitating nature, but because the physics that makes nature round also applies to anything we build. Let's talk about exotic forms of matter and whether they would be round. We've been mostly talking about ordinary matter, atoms, molecules, gas, dust, rock, metal. But there are exotic forms of matter in the universe. Neutron stars, for example, are made of neutronium, matter compressed so densely that protons and electrons have merged into neutrons. It's the densest, stable form of matter we know of. And neutron stars are round. They're oblate if they spin fast, but they're still basically spherical. Even though neutronium has weird properties, very different from ordinary matter, it still responds to gravity, and gravity still pulls it into a sphere. What about dark matter? Dark matter is this mysterious stuff that makes up about 85% of the matter in the universe. We don't know what it is. We can't see it directly. We only know it exists because of its gravitational effects. Dark matter doesn't interact with light or normal matter except through gravity. But it does interact with itself gravitationally. And what shape does dark matter take? Interestingly, dark matter forms roughly spherical halos around galaxies. These halos are called dark matter halos, and they're much larger than the visible galaxies themselves. The Milky Way is embedded in a dark matter halo that extends hundreds of thousands of light years from the galactic center. Why are dark matter halos spherical? Same reason: gravity. Dark matter collapses under its own gravity, just like normal matter. And when something collapses under gravity in a spherically symmetric way, you get a sphere or an oblate spheroid if it's rotating. Actually, dark matter halos are often slightly triaxial, meaning they're slightly ellipsoidal with 3 different axis lengths. This happens because dark matter doesn't collide or dissipate energy the way normal matter does. Normal matter can radiate energy and settle into a nice flat disk or perfect sphere. Dark matter just falls under gravity and reaches a more complex equilibrium. But even so, dark matter halos are still roughly round, roughly ellipsoidal. They're not wildly irregular. So even this exotic, invisible form of matter that we barely understand still follows the same basic principles. Gravity pulls it together and it forms roughly round structures. Let's talk about the cosmic web. On the very largest scales, the universe has structure. Galaxies aren't randomly distributed. They're arranged in a vast cosmic web of filaments and sheets surrounding enormous voids. This is called the large-scale structure of the universe. And what determines this structure? Gravity. After the Big Bang, matter was distributed almost uniformly, with tiny variations. Over billions of years, gravity amplified those variations. Denser regions attracted more matter and became denser still. Underdense regions lost matter to the surrounding denser regions and became voids. The result is a foam-like structure, long filaments where galaxies are concentrated surrounding vast empty voids. And what shape are the voids? They're roughly spherical or ellipsoidal. Because as matter flows out of underdense regions toward overdense regions, it flows in all directions, carving out roughly round voids. So even on the largest scales, the scale of the entire observable universe, we see roundness emerging from gravity. The voids are round. The galaxy clusters at the nodes of the cosmic web are roughly round. It's spheres all the way up and all the way down. Let's come back to Earth and think about mountain ranges and ocean basins because they seem like exceptions to roundness. Earth is round overall, but its surface has dramatic features. Mountains rise miles above sea level. Ocean trenches plunge miles below. Doesn't this contradict the idea that gravity makes things round? Not really. Earth is round when you look at it from space, but when you're standing on the surface, the local irregularities are significant. But here's the key. There's a limit to how high mountains can be. Gravity sets that limit. If a mountain gets too high, the rock at the base can't support the weight above it. The rock will flow or fracture, and the mountain will collapse. On Earth, the tallest mountain, Mount Everest, is about 29,000 feet above sea level. But measured from the center of Earth, it's not the farthest point from the center. That honor goes to Mount Chimborazo in Ecuador, because Chimborazo is closer to the equator where Earth bulges out. The point is, mountains can only get so tall before gravity limits them. And compared to Earth's radius of about 4,000 miles, even the tallest mountains are tiny perturbations. Earth is round to within about 0.5%. That's actually pretty spherical. On smaller planets with weaker gravity, mountains can be taller. Mars's Olympus Mons is about 69,000 feet tall, more than twice the height of Everest. Mars has about 1/3 Earth's gravity, so rocks can be piled higher before they collapse. On asteroids with even weaker gravity, you can have very irregular shapes with features that would be impossible on larger bodies. But there's a trade-off. Smaller bodies don't have enough gravity to be round in the first place. So you get irregular asteroids with dramatic features, or you get round planets with limited topography. Either way, gravity is determining the shape. So the takeaway from all of this, from everything we've discussed, is that roundness is a natural consequence of gravity operating in a symmetric way. When you have mass, and gravity pulls that mass toward a center point, and gravity acts equally in all directions, you get a sphere. It's inevitable. It's mathematical. It's beautiful. We see spheres everywhere in the universe because the universe is governed by simple symmetric laws. Gravity doesn't care which direction you're looking. It pulls equally in all directions, and the result is spherical symmetry. Throw in rotation, and you get oblate spheroids. But the basic theme remains: roundness. From raindrops to planets to stars to galaxies to black holes to the voids in the cosmic web, we see the same pattern repeating at every scale. It's one of the most fundamental patterns in nature, and it all comes down to gravity, energy minimization, and symmetry. So the next time you look at the moon or the sun or a planet in the night sky, appreciate that you're seeing the handiwork of gravity. You're seeing the universe solving an optimization problem. How do you arrange matter to minimize energy? The answer is a sphere. And the universe has been solving that problem over and over again for nearly 14 billion years. That's why almost everything in the universe is round. Not because of some cosmic decree or design, but because of simple physical principles playing out over cosmic timescales. Gravity pulls, matter falls, spheres form. It's that simple and that profound. And there's something deeply satisfying about understanding this. We live in a universe that makes sense, a universe governed by comprehensible laws, a universe where the same principles apply everywhere, from the smallest scales to the largest. That's the real miracle. Not that things are round, but that we can understand why they're round. Thank you so much for watching this deep dive into the roundness of the universe. If you enjoyed this video, please hit that like button, subscribe if you haven't already, and let me know in the comments what cosmic mystery you want me to tackle next. There's so much more to explore about how the universe works, and I'm excited to share that journey with you. Until next time, keep looking up, keep asking questions, and keep marveling at the incredible universe we live in. Retry, you continue. And before we wrap up, I want to dig even deeper into some of the implications and fascinating details we haven't fully explored yet, because this topic really opens up into so many different areas of physics and astronomy. Let's talk about what happens during planetary formation in more detail. Because the process of going from a cloud of dust to a round planet is absolutely fascinating, and it perfectly illustrates all the principles we've been discussing. When a new star forms from a collapsing cloud of gas, it doesn't capture all the material. There's leftover gas and dust that ends up orbiting the young star in what we call a protoplanetary disk. This disk is where planets form, and the process starts with dust grains. Tiny particles maybe a micrometer across, smaller than the width of a human hair. These dust grains are floating around in the disk, orbiting the star, and occasionally they bump into each other. When they do, sometimes they stick together through van der Waals forces or electrostatic attraction. It's the same force that makes dust stick to your TV screen. These tiny forces are enough to make microscopic grains stick together. So grain by grain, these particles grow. A micrometer becomes 10 micrometers, 10 becomes 100, 100 becomes a millimeter. You're building up these little clumps of dust, and as they grow, their gravity becomes slightly stronger. Not much, but a little bit. And that tiny bit of gravity helps them capture even more dust when they collide with other particles. This process continues, and you start to get pebbles, then rocks, then boulders, then kilometer-sized planetesimals. And all of this is happening in orbit around the young star. These objects are colliding, sometimes sticking together, sometimes breaking apart. It's a violent, chaotic process. The early solar system was like a shooting gallery, with objects crashing into each other constantly. But here's where it gets interesting from our roundness perspective. When these planetesimals are small, just a few kilometers across, they're irregular shaped. Gravity isn't strong enough to round them out. They look like the asteroids we see today, lumpy and potato-shaped. But as they keep growing, as they accumulate more and more mass, their gravity gets stronger and stronger. Eventually, you reach a critical point. The object has enough mass that its gravity is strong enough to overcome the structural strength of rock. And at that point, the object starts to deform. The tallest mountains get pulled down. The deepest valleys get filled in. The whole object starts to flow very slowly like a very thick fluid until it reaches a spherical shape. This process is called differentiation, and it's crucial for planetary formation. When a planetesimal gets big enough and hot enough, the interior starts to melt or at least soften. And when it does, the denser materials sink toward the center and the lighter materials float toward the surface. In Earth's case, iron and nickel sank to the core, while lighter silicate rocks formed the mantle and crust. And as this differentiation happens, the object becomes spherical. The molten or semi-molten interior can flow in response to gravity, and gravity always pulls toward the center. So the object naturally assumes a spherical shape. It's the path of least resistance, the minimum energy configuration. Now, this process takes time. For a planet the size of Earth, differentiation probably took tens of millions of years, but that's nothing on geological timescales. And once the planet cooled and solidified, it retained its spherical shape. Even though the interior is no longer molten, even though the crust is solid rock, the planet stays round because that's the shape gravity gave it when it was forming. Let's talk about the really early universe again, but in more detail about structure formation. I mentioned that tiny quantum fluctuations in the early universe were the seeds of all structure, but let's really dive into what that means. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called inflation. During inflation, quantum fluctuations, tiny random variations in energy density at the quantum scale, were stretched to macroscopic sizes. These fluctuations became variations in the density of matter and energy across space. After inflation ended, the universe continued expanding, but at a slower rate, and those density fluctuations remained, imprinted on the distribution of matter. Regions that were slightly denser than average had slightly stronger gravity. And over time, those denser regions attracted more matter from their surroundings. This process is called gravitational instability, and it's how structure grew in the universe. The denser regions got denser, the underdense regions got emptier. And this process operated on all scales simultaneously. Small fluctuations grew into stars. Medium fluctuations grew into galaxies. Large fluctuations grew into galaxy clusters and superclusters. And at each scale, as matter collapsed under gravity, it formed roughly spherical structures. Or actually, more precisely, it formed dark matter halos that were roughly spherical, and then normal matter fell into those halos and formed stars and galaxies. The beautiful thing is that we can actually observe this process happening. We can look at galaxies at different distances, which means different times in the past because light takes time to travel. Distant galaxies show us what galaxies looked like billions of years ago. And we can see that galaxies in the early universe were smaller and more irregular than galaxies today. They were still in the process of forming and merging. But even those early, irregular galaxies were made of round stars. The stars formed first from local collapses of gas clouds. And stars are always round because gravity always pulls gas into spheres. So even in a chaotic young universe, roundness was already emerging at the stellar scale. Let's talk about resonances and orbital mechanics, because this is another area where roundness plays a crucial role. When planets orbit a star, they're not just moving in isolation, they're gravitationally interacting with each other. And sometimes, these interactions can lock planets into resonant orbits. A resonance happens when the orbital periods of two planets have a simple integer ratio. For example, Neptune and Pluto are in a 3:2 resonance. For every 3 times Neptune orbits the Sun, Pluto orbits twice. This resonance is stable and protects Pluto from close encounters with Neptune, even though Pluto's orbit crosses Neptune's. Resonances like this arise naturally in systems of orbiting bodies, and they're possible because orbits are approximately elliptical, which is itself a consequence of the spherical symmetry of gravity. If planets weren't roughly spherical, if their gravitational fields were irregular, orbital mechanics would be much more chaotic and resonances might not be stable. The moons of Jupiter show beautiful examples of resonances. The moons Io, Europa, and Ganymede are locked in a 1-2-4 resonance. For every orbit Ganymede makes, Europa makes 2 and Io makes 4. This resonance is called the Laplace resonance, and it has profound effects on these moons. The resonance causes the moons to gravitationally tug on each other in a regular pattern. These tugs prevent the orbits from becoming perfectly circular. The orbits remain slightly elliptical. And as the moons move along these elliptical orbits, the tidal forces they experience from Jupiter vary. Sometimes the moon is closer to Jupiter and feels stronger tides. Sometimes it's farther and feels weaker tides. This varying tidal stress flexes the interior of the moon, generating heat through friction. This is called tidal heating. And in Io's case, the tidal heating is so intense that Io is the most volcanically active body in the solar system. Io has hundreds of active volcanoes constantly erupting, all because of this resonance, which exists because of the regular round orbits determined by spherical gravity. Europa also experiences tidal heating, though not as intensely as Io, and this tidal heating might keep a liquid water ocean beneath Europa's icy surface. This ocean is one of the best places in the solar system to look for life beyond Earth, and it exists because of tidal heating, which exists because of orbital resonances, which exist because of the spherical symmetry of gravity. So roundness isn't just about shapes, it's deeply connected to orbital dynamics, tidal effects, heating, volcanism, and potentially even the existence of habitable environments. The roundness of planets enables all these other phenomena. Let's talk about what we can learn from shapes. When we observe celestial objects, their shapes tell us about their history. A round object tells us it's been massive enough for gravity to shape it, and probably old enough to have relaxed into equilibrium. An irregular object tells us it's small or young or has experienced recent disruption. Take Pluto's moon Charon. Charon is round, which tells us it's massive enough to be in hydrostatic equilibrium. But the Pluto-Charon system is unusual. Charon is so large compared to Pluto that they're sometimes called a binary dwarf planet system. They're tidally locked, not just with Charon always showing the same face to Pluto, but also with Pluto always showing the same face to Charon. They orbit around a common center of mass that's actually outside Pluto's surface. This mutual tidal locking tells us about the history of the system. The tides have been working on both bodies for billions of years, gradually slowing their rotations until they became locked. And both bodies are round, which tells us they were both big enough to be shaped by gravity when they formed. Their roundness is evidence of their size and age. Or consider comets. Most comets we've visited with spacecraft are irregularly shaped. This tells us they're small and they've never been heated enough to flow and round out. But it also tells us something else. These comets are probably primordial objects, unchanged since the early solar system. They're frozen relics that have preserved their original shapes for billions of years. When we visited Comet 67P with the Rosetta mission, The irregular, rubber-ducky shape told us immediately that this comet was probably formed from two objects that gently merged. The low-speed collision didn't generate enough heat to melt the ice and allow the comet to round out. So we're seeing the original shapes of two planetesimals from the early solar system, stuck together and preserved for 4.5 billion years. That's the power of understanding shapes. Shapes are records of history, frozen in stone and ice. Let's talk about theoretical objects in extreme physics. What about quark stars? These are hypothetical objects even denser than neutron stars. In a neutron star, protons and electrons have merged into neutrons. But if you compress matter even further, the neutrons themselves might break apart into their constituent quarks. The result would be a quark star, made of a soup of free quarks. Would a quark star be round? Almost certainly. Quark matter would still respond to gravity, and gravity would still pull it into a sphere. The equation of state would be different, the relationship between pressure and density would be different, but the fundamental principle would be the same. Gravity pulls inward, pressure pushes outward, equilibrium is reached, and the result is a sphere. What about even more exotic objects? Hypothetical strange matter made of up, down, and strange quarks. Hypothetical preon stars, if quarks themselves are made of smaller particles. Black stars, hypothetical alternatives to black holes. In all cases, as long as these objects are held together by gravity and as long as gravity acts the same way it does in general relativity, they'd be round. The only way to get non-round objects at large scales would be if gravity itself worked differently. If space-time had weird properties, if there were extra dimensions with different geometries, if gravity had directional preferences, then maybe you could get non-spherical massive objects. But in our universe with our physics, roundness is inevitable for anything big enough. Let's think about information and roundness. There's a concept in physics called the holographic principle, which suggests that all the information contained in a volume of space can be encoded on the boundary of that volume. This principle arose from studying black holes and their entropy. Black holes have entropy proportional to the area of their event horizon, not their volume. This is weird because usually entropy scales with volume. But for black holes, it scales with surface area. And since black holes are round, their surface area is just 4 pi r squared, where r is the radius of the event horizon. This connection between information, entropy, and the surface area of a sphere is profound. It suggests that at the deepest level, even information itself might be connected to the spherical geometry of spacetime around massive objects. The roundness of black holes isn't just a geometric fact. It might be telling us something fundamental about the nature of information and reality. But I'm getting pretty speculative here. Let's come back to things we can observe and measure. Let's talk about how we use the roundness of objects for science. One of the most important techniques in astronomy is called gravitational microlensing. When a massive object passes in front of a more distant star, the massive object's gravity bends the light from the background star. This bending acts like a lens, magnifying and distorting the image of the background star. The pattern of magnification depends on the mass and shape of the lensing object. If the lensing object is perfectly spherical, you get a characteristic light curve, a graph of brightness over time that has a specific shape. Any deviation from spherical symmetry shows up as an anomaly in the light curve. We've used this technique to discover exoplanets. When a planet passes in front of a background star along with its host star, the planet's gravity creates a small blip in the lensing light curve. And the shape of that blip tells us about the planet's mass. The technique assumes the planet is roughly spherical, which is a safe assumption for any planet large enough to be detected this way. We've also used microlensing to search for dark matter. If dark matter is made of massive compact objects, sometimes called macos, these objects would occasionally lens background stars. The fact that we haven't seen as many lensing events as we'd expect if dark matter were made of macos tells us that dark matter is probably not made of large compact objects. It's probably something else, maybe fundamental particles that don't clump into massive spheres. So even our search for dark matter depends on understanding what shapes massive objects should have. Let's talk about time and how shapes change over time. Nothing in the universe is truly static. Everything is evolving. Stars are burning fuel and changing. Planets are cooling and their interiors are solidifying. Galaxies are merging and reshaping. Even black holes are evaporating, incredibly slowly, through Hawking radiation. Over time, these evolutionary processes change shapes. A young star might be more oblate than an old star because young stars spin faster. As stars age, they lose angular momentum through stellar winds, and they slow down, so they become more spherical over time. A young galaxy might be irregular and chaotic, full of star formation and violent activity. Over billions of years, it settles down, uses up its gas, and becomes a smooth, elliptical galaxy. The shape evolution is a record of the galaxy's history. Earth itself has changed shape over its history. When Earth was young, it was hotter and spinning faster. It was more oblate than it is today. As Earth cooled and slowed down, it became more spherical. And Earth's interior is still slowly churning, still slowly evolving. The shape we measure today is a snapshot of an ongoing process. Even the universe as a whole is evolving. The expansion of the universe is governed by the distribution of matter and energy, and that distribution has changed over time. In the early universe, matter was more uniformly distributed. Over time, structure has grown. The cosmic web has become more pronounced. Voids have become emptier. Filaments have become denser. And if you could measure the shape of the universe, the overall geometry of space-time, that shape might be evolving too. Current observations suggest the universe is spatially flat or very close to flat. But there's always some uncertainty in the measurements, and the curvature might be changing as the universe expands and the density of matter and dark energy changes. So even at the largest scale, the scale of the entire universe, shape is a dynamic thing, evolving over cosmic time. Let's talk about the human perspective on all this. For most of human history, people didn't know that planets were round. They looked like points of light in the sky. Even the moon, which is obviously not a point of light, didn't obviously look spherical to ancient peoples. It took careful observation and reasoning to figure out that the moon and planets were round. The ancient Greeks figured it out through clever reasoning. Aristotle argued that the moon must be spherical because its shadow on the sun during solar eclipses was always circular. He also noted that Earth's shadow on the moon during lunar eclipses was circular, suggesting Earth itself was round. Eratosthenes measured the circumference of Earth by comparing the angle of shadows at different latitudes. He realized that if Earth was curved, shadows would fall at different angles at different locations, and they did. From this, he calculated Earth's circumference to remarkable accuracy over 2,000 years ago. But it wasn't until the space age that humanity actually saw planets as round objects. The first pictures of Earth from space, especially the famous blue marble photo from Apollo 17, showed us our planet as a beautiful blue sphere floating in the blackness of space. Those images had a profound psychological impact. They showed us viscerally that Earth is round, finite and fragile. And as we've sent spacecraft to other planets, we've seen their roundness too. The beautiful spheres of Jupiter with its swirling clouds, the pale disk of Uranus tipped on its side, the deep blue of Neptune, the reddish globe of Mars. Every image confirms what physics predicts: planets are round. There's something humbling about them. The forces that shape planets are the same forces that govern everything in the universe. We're not special. Our planet is round for the same reason every other planet is round. We're part of a universal pattern. But there's also something empowering about understanding this. We can look at a distant exoplanet, hundreds of light years away, and confidently say it's probably round. We can predict the shapes of objects we've never seen, in places we'll never visit, based on our understanding of physics. That's the power of science. Let's talk one more time about what roundness really means at the deepest level. Roundness is symmetry. Specifically, it's spherical symmetry. A sphere looks the same from any direction. Rotate it any way you want, and it looks the same. This is called isotropy. And the universe itself, on the largest scales, appears to be isotropic. The cosmic microwave background, the afterglow of the Big Bang, is almost perfectly uniform in all directions. Galaxies are distributed roughly uniformly in all directions when you average over large enough scales. The universe doesn't have a preferred direction. This isotropy at the largest scale is reflected in the isotropy at smaller scales. Planets are round because gravity is isotropic. Stars are round because pressure gradients are isotropic. Black holes are round because space-time curvature is isotropic. It's symmetry all the way down and all the way up. And this symmetry is a clue to the fundamental laws of physics. Physicists love symmetry because symmetries are connected to conservation laws through Noether's theorem. Time symmetry gives us conservation of energy. Space symmetry gives us conservation of momentum. Rotational symmetry gives us conservation of angular momentum. The roundness we see everywhere is a manifestation of these deep symmetries. It's not just that things look round, it's that the laws of physics themselves have a spherical symmetry that gets expressed in the shapes of objects. And that brings us full circle, back to where we started. Why is almost everything in the universe round? Because gravity pulls equally in all directions, because systems minimize their energy, because the laws of physics are symmetric, because the universe makes sense. Every sphere we see, from raindrops to planets to stars to galaxies, is a testament to these principles. They're all solving the same optimization problem: how to arrange matter under the influence of gravity. And the answer, over and over again at every scale in every corner of the universe, is the same: a sphere. That's the profound beauty of it. That's why I find this topic so endlessly fascinating. It's not just about shapes. It's about the fundamental nature of reality. It's about the elegant simplicity underlying the apparent complexity of the universe. It's about how the same simple rules applied over and over create the magnificent cosmos we see around us. So the next time someone asks you why planets are round, you can give them the simple answer: gravity. But now you know there's so much more to it than that. There's the history of planetary formation, the physics of hydrostatic equilibrium, the effects of rotation, the role of tidal forces, the connection to orbital mechanics, the evolution over time, the relationship to symmetry and conservation laws, and the fundamental structure of space-time itself. It's all connected. Everything in physics is connected, and the roundness of the universe is a beautiful thread running through all of it, tying together concepts from classical mechanics to general relativity to quantum field theory to cosmology. We've covered so much ground in this video, from dust grains to the cosmic web, from soap bubbles to black holes, from the early universe to the distant future. And through it all, one theme has remained constant. Roundness emerges naturally from the laws of physics. It's inevitable, it's universal, and it's beautiful. I hope this deep dive has given you a new appreciation for the shapes we see in the sky. I hope the next time you look at the moon or watch the sun set or gaze at Jupiter through a telescope, you'll think about the incredible physics that shape those spheres. You'll think about gravity collapsing clouds of gas, about spinning matter flattening into disks, about tidal forces stretching and squeezing, about the universe endlessly solving its optimization problems. And maybe you'll feel what I feel, a sense of wonder at how comprehensible the universe is. We're just humans, living on one small round planet, orbiting one ordinary star in one galaxy among hundreds of billions. And yet, we've figured out why things are round. We've unraveled one of the universe's patterns. That's extraordinary. Thank you for sticking with me through this entire journey. This has been a marathon exploration of roundness, gravity, and the structure of the cosmos. I hope you've learned something. I hope you've been inspired. And most of all, I hope you'll keep asking questions about the universe, because every question leads to new insights, new connections, new beauty. Keep exploring, keep wondering, keep looking at the round universe around you and marveling at the simple elegance of the laws that shaped it. Until next time, stay curious and remember, we live in a universe that makes sense if we just take the time to understand it.
Free audio post-production by alphonic.com.